All right, so in part 12, we're going to be looking at some more details of function behavior. We're going to be looking here at where functions are increasing, decreasing, and constant. And here I have the very formal definition of what that is, but I think it's best to look at a picture to really talk about what we mean here. If we're talking about an increasing function, moving from left to right, that function is getting larger. It's kind of following a positive slope value. Now, we can talk about where a function is increasing, and the function might not be increasing everywhere. It might just be increasing for part of it. We can talk about where it's decreasing or it's falling, and where it's constant. When we are talking about where a function is increasing, decreasing, and constant, we're talking about describing it using x values. So we're not talking about describing the y values, we're only talking about x values. So it says state the intervals, again referring to x, on which each function is increasing, decreasing, or constant. So if we look at this function, we're always looking from least to greatest on our domain, on our x-axis here. So as we move from left to right, when we start to see this function, it's decreasing, and we can assume it continues doing that forever and ever on to negative infinity. So, and I'll go ahead and just put little ending arrows here indicating that it's going further in that direction and further in that direction. We see that this function is decreasing, 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 decreasing. And here it stops decreasing. And we're not looking at the y value here, we're looking at the x value. And it's hard to tell on the camera here. Let me zoom in a tad, see if I get a better, clearer picture here. But on your paper, hopefully you can see this grid, and it looks like it's right between 1 and 2. So we'll say that's about 1.5. So this function is decreasing from negative infinity all the way to an x value of 1.5. And then from 1.5, it starts to increase. And now it's increasing, 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 and then it stops. And again, on your paper, hopefully you can see greater detail here. This looks to be about 4.5. So it's increasing from 1.5 all the way to 4.5. And then it starts decreasing again forever and ever, goes down forever and ever. So it's decreasing again. You can either use a comma or you could use the union symbol from 4.5 to infinity. And there is no area where it's constant. Okay. The next example, we have what's called a piecewise function, and we've seen one of these once before, and we're going to look closer at piecewise functions in just a second here. Let's again assume that this goes on forever in this direction and forever in this direction here. And if I want to state the areas where it's increasing, decreasing, and constant, we can tell here from going off to infinity from least to greatest, negative infinity all the way until negative 1, it is constant. Now, we're always using parentheses, we're never using brackets, so even if you see open and closed dots, at that single point, it's not either one. It's ending one thing, moving on to the next. So we'll always be using parentheses when we're describing where a function is increasing, decreasing, or constant. And then we see from here, it starts to go down. So we went from negative infinity all the way to negative 1, and then it stopped being constant. And then it started to decrease, but it only decreases a little bit, and then it starts to increase. So decreasing from negative 1 to 0, from negative 1 to 0, and then from 0 to infinity, it is increasing. So to infinity, this will keep increasing. Okay. One of the other details we can look at in function behavior is the maximum, the relative minimum and maximum. So when we're talking about relative minimums and maximums, what we're looking at here is values like what we're seeing in this last example, where everything around this point is above it. That would be a minimum value. every other immediately neighboring point is above it. Similarly, in the example we did first, we can see a maximum right here. This is a maximum point because every other point immediately neighboring it is below it. Even though there's points higher over here, this is still a relative maximum. It is not an absolute maximum. This graph that we're looking at up here, because it goes up forever and ever and ever, it does not have an absolute maximum, but it does have a relative maximum. All right, so that's one other way we can talk about the behavior of a function. We can also use or determine whether a function is even or odd. So even functions, the original function is going to be equal to if we plugged in negative x for x. And again, this is a concept that's easier to understand through doing an example. Odd functions, if we took the original function and we multiplied it by -1, that would be equal to plugging in negative x. So we are going to look at how to do that algebraically. So these examples here say determine whether each of the following functions are even, odd, or neither. And this function here says f of x is equal to x cubed minus 6x. So the first thing that we will always check is going to be if it's even. So if it's even, then f of x will be equal to f of negative x. So we want to find that first. And what that means is we're plugging in negative x everywhere there's an x. Simplifying that, negative x cubed is negative x cubed, and negative 6 times negative x is plus 6. And this is definitely not equal to the original equation. So it's not even. Then we want to find, okay, what is negative f of x? And that's like multiplying a -1 times the whole function. Well, -1 times all of this gives me negative x cubed plus 6x. And if these two are equal, then that means it's odd. Okay? As long as those two are equal. F of negative x and negative f of x. The next example is g of x equals x to the 4th power minus 2x squared. And again, first we will check if it's even. So let's find f of negative x. So if I plug in negative x to the 4th power, that gives me just x to the 4th power. And negative x squared is just x squared, so minus 2x squared. And that is equal to the original, so that means that this is an even function. Once we determine it's even, we don't even need to bother checking about odd because it won't be both. The last one here, we have h of x is equal to x squared plus 2x plus 1. And we want to go ahead and first check if it's even. Plugging in negative x, we have negative x squared plus 2 negative x plus 1. And we want to see, is that equal to the original? Negative x squared is x squared. 2 times negative x is negative 2x plus 1. Well, it's really close, but it's off by 1 sign. So they're not equal. That means this is not even. Let's try negative h of x and see if that's equal to this. Well, multiplying it out, we can see that this is not equal to this, so that means it's not odd either. It means it's neither even nor odd. Or you could just write neither. On a quiz or an exam, what I would want to see for these kinds of questions is all of the work you're seeing here. Writing odd, even, or neither without any work at all doesn't get you any points, even if you're correct, because anybody can guess odd, even, or neither. What you want to do is make sure you're showing why it's odd or why it's even, or why it's neither. All right, so we're going to do one more example here. Actually, I think we're going to do two more examples of what are called piecewise functions. Now, we've seen piecewise functions a little bit, but we haven't actually graphed one ourselves. So a piecewise function is really just a function that is defined by two or more equations over specific domains. Meaning, I'm going to say we're going to graph this function, but just in this area. And we're going to graph this function, but just in this area. And this function, but just in this area. So, let me go ahead and set up our graph real quick here. Now, I think this is helpful to do in different colors. You're welcome to do that as well, or you're welcome to just do all of it in the same. But I'm going to graph this function here in this light blue color. And negative x minus 1. If I were to graph that just by itself, I would use my y-intercept at negative 1. And then my y-intercept from there, I have a slope of negative 1, so I could go up 1 and over 1 this direction, so it's a negative slope, or I could go down this direction. But this function is only defined where x is less than negative 1. So you kind of divide your graph here. This is where x is less than negative 1. So I only want this function graphed from here and over, where it's less than negative 1. So even though my y-intercept is at negative 1, and then I would go up 1 over 1 and I would plot a point, it's not equal to there. There's no line underneath it. So I'm going to go ahead and plot that point, but with an open dot. And then I can keep plotting points, up 1 over 1, up 1 over 1, up 1 over 1. And these are all less than negative 1, so I can actually close those dots. This next part I'm going to do in green. And that's just the constant function negative 3. So at negative 3, that would be a horizontal line. But we only want this from negative 1 to 2. So if you just imagine this part of our graph, just between negative 1 and 2, I want that constant function of negative 3. Now it's equal to at negative 1, but not at 2. So I'll have an open dot at 2 and a closed dot at negative 1. And then the last one, the square root function. Now this means it's shifted to the right 2. So this, if you think about the square root graph that we graphed previously, and it looked kind of like that, it's been shifted to the right 2. The other thing you can do is you can plug in some points. It's equal to 2, has the equal to sign. So if I plugged in x equals 2, well, 2 minus 2 would be 0. Okay, closed dot there. I could plug in 3. 3 minus 2 would be 1. The square root of 1 would be 1. If I plugged in 4, 4 minus 2 would be 2, and we don't know that square root. So I'm going to plug in something that I know. 6 minus 2 is 4, and I know the square root of 4. So if I plug in 2, 3, 4, 5, 6, 6 minus 2 is 4. Square root of 4 is 2. I can go ahead and continue that graph. So that was how you would go ahead and graph a piecewise function. We're going to do one more example of graphing a piecewise function. Oh, you know what? We aren't done with that one. In addition to graphing, this question also asks us to find some values. Now you can do this just from the equation, or you can do this using your graph, and I'm going to do both so you can see that both of them will give us the same answer. If I want to find f of negative 3, I need to figure out which interval that falls into. Well, negative 3 is less than negative 1, so I would use this equation. If I plug in negative 3 times the negative would be positive 3. Positive 3 minus 1 would be 2. We can also use that from our graph. If I go to my graph and I look at negative 1, negative 2, negative 3, my graph gave me a value of 2. 2, well, x is not equal to here. It just is strictly less than. But x is equal to 2 here. And so I could plug into my equation. 2 minus 2 is 0. Square root of 0 is 0. Or I could look at my graph at x equals 2, and in fact I do see that it's equal to 0. Negative 1. Well, negative 1 is not equal to here. It's strictly less than negative 1, but it is equal to here. So I could go to this equation, but there's no x value for me to plug into. It's just negative 3. If I got 0 in this interval, it would be equal to negative 3. If I got positive 1 in this interval, it would be negative 3. Anything between negative 1 and 2 is going to give me a value of negative 3. And if I plug in 6, again, 6 is greater than 2, so I could plug in here. 6 minus 2 is 4, square root of 4 is 2, or I could look at my graph. Okay. All right, one more example of working with piecewise functions, and then that'll bring us to the end of this video. This next example, let me set up my graph first, actually. So we just have two equations here. It says x is less than negative 1. So again, I always like it kind of doing this. I think it's helpful just to visualize, okay, I just want that one on this side of negative 1. And that's the function x plus 3. So I would go up to my y-intercept of 3 and a positive slope of 1, but I don't want to go that way. I want to go the other way. So y-intercept of 3, down 1 over 1. And it's not equal to, but I can go ahead and plot a point there with an open dot. And then down 1 over 1, down 1 over 1. I can keep doing that many times as I want to. So that was this function here. And then here I have the x squared function from negative 1 all the way to 2. And then it ends there. My graph doesn't keep going forever. So if I were to plug in some values, or I could use the parent graph that we saw earlier. If I plugged in a couple values here, and I plugged in, it's equal to negative 1, 0, and 1. Well, if I plug in negative 1 squared is 1. If I plug in 0, it's 0. If I plug in 1, it's 1. But it goes all the way to 2, and if I plug in 2 squared is 4. But because it doesn't equal it, I can't put a closed dot there, but I do need to put an open dot there because it goes all the way up to 2, but doesn't actually touch it. Okay, that's why I have that open dot there. Now it says find these values here, so let's go ahead and find those. F of negative 3, F of 2, and F of negative 1. Well, negative 3 is less than negative 1. Negative 3 plus 3 would be 0. 2, well, it's definitely not less than negative 1. And here it's not equal to 2. And then my function just stops after that. So that would be undefined, or the empty set, or D and E does not exist. Any of those would be fine. And then negative 1. Well, it's not equal to negative 1 here, but it is equal to negative 1 here, and negative 1 squared is 1. Okay. We're going to go ahead and end this video here, and then we'll be picking up with part 13 next.